Right now, at the center of our galaxy, something with the mass of 4 million suns is pulling every star around it in a perfect dance, and it's completely invisible. This invisible monster isn't just sitting there doing nothing. It's actively controlling the birth and death of stars across our entire galaxy. And here's the crazy part. Without it, we wouldn't exist. Black holes are usually thought of as cosmic destroyers, things that eat everything and give nothing back. But that's only half the story. The truth is that black holes are actually master architects of the universe. They're quietly building and shaping galaxies in ways we're just starting to understand. And when I say quietly, I mean they're doing this over millions and billions of years, working behind the scenes while we go about our daily lives completely unaware. Here's what's strange about this whole thing. For decades, scientists couldn't figure out why galaxies look the way they do. Why do some galaxies have perfect spiral arms while others are just messy blobs of stars? Why do some galaxies stop making new stars while others keep pumping them out like factories? And most puzzling of all, why does the black hole at the center of a galaxy seem to know exactly how big the galaxy around it should be? Think about that for a second. A black hole that takes up basically zero space compared to its galaxy somehow controls stars that are thousands of light years away from it. It's like a grain of sand somehow, controlling the entire beach it sits on. This doesn't make sense according to what we thought we knew about gravity and physics. But here's where it gets even more mysterious. When astronomers started measuring black holes and their galaxies, they found something incredible. There's a perfect relationship between how massive a black hole is and how massive the bulge of stars around it. Island every single time. This relationship is so precise that if you know the mass of a galaxy's central bulge, you can predict the mass of its black hole with scary accuracy. This discovery completely changed how we think about black holes and galaxies. It means they're not separate things that just happen to live in the same neighborhood. They're connected. They talk to each other. They influence each other. And most importantly, they grow up together like cosmic twins. Let's start with how this whole relationship begins. Picture the early universe, about 13 billion years ago. Space was a much more chaotic place back then. Matter was clumping together under its own gravity, forming the first structures in the universe. Some of these clumps became the seeds of future galaxies. Others became the seeds of future black holes. Now, here's what's fascinating about this process. The black hole seeds and galaxy seeds weren't forming in isolation. They were forming from the same clouds of gas and dust. So, right from the very beginning, their fates were tied together. As more matter fell into these regions, some of it fed the growing black hole, while some of it formed new stars in the growing galaxy. But this is where things get really interesting. As matter falls into a black hole, it doesn't just disappear quietly. Before it crosses the point of no return, it gets heated up to incredible temperatures. We're talking about temperatures of millions of degrees. This superheated matter glows so brightly that it can outshine the entire galaxy around it. These glowing disks of doomed matter are called accretion disks. Now, you might think that all this matter just falls into the black hole, and that's the end of the story. But that's not what happens. The extreme temperatures and magnetic fields around the black hole create something incredible. They launch jets of particles and energy at nearly the speed of light. These jets shoot out from the poles of the black hole, extending for thousands of light years into space. These jets are like cosmic pressure washers. They blast through the gas and dust in the galaxy, heating it up and pushing it around. This has a huge impact on star formation because stars need cold, dense gas to form. When the black hole jets heat up all the available gas, star formation slows down or even stops completely. This is how black holes regulate their galaxies. When a galaxy has lots of gas available and is forming stars rapidly, more matter falls into the central black hole. This makes the black hole more active, which creates stronger jets, which heat up more gas, which slows down star formation. It's like a cosmic thermostat keeping everything in balance. But the relationship goes even deeper than that. Recent computer simulations have shown us that black holes can actually trigger star formation in certain circumstances. When those powerful jets slam into dense clouds of gas, they can compress the gas enough to kickstart new star formation. So, black holes aren't just destroyers of star formation, they can also be creators. This dual nature of black holes makes them incredibly important for galaxy evolution. They can turn star formation on or off like a switch, depending on what the galaxy needs. Too much star formation, the black hole cranks up its activity and cools things down. Too little star formation, the black hole might trigger new waves of starbirth through its jets. Let's talk about what this looks like on a galactic scale. Our own Milky Way galaxy is a perfect example of this black hole galaxy partnership in action. At our galactic center sits Sagittarius A, a black hole with a mass of about 4 million suns. Now that might sound massive, but compared to our entire galaxy, it's tiny. The Milky Way contains over 100 billion stars, many of which are more massive than our Sun. Yet, despite being so relatively small, Sagittarius A has been shaping our galaxy for billions of years. The orbits of stars near the galactic center are completely determined by this black hole's gravity, but its influence extends much further than just the nearby stars. Throughout the galaxy's history, Sagittarius A has gone through periods of high activity and low activity. When it was more active in the past, it would have launched powerful jets that influenced star formation across huge regions of the galaxy. Evidence of this ancient activity can still be seen today in the form of giant bubbles of hot gas extending above and below the galactic plane. These structures, called the Fermi bubbles, stretch for about 25,000 light years in each direction from the galactic center. They're the leftover signatures of massive outbursts from our central black hole that happened millions of years ago. These outbursts would have significantly affected the environment for star formation across large parts of our galaxy. But Sagittarius A isn't unique in this behavior. Astronomers have found evidence of similar black hole feedback in galaxies throughout the universe. Some galaxies show clear signs of recent black hole outbursts that have completely shut down star formation. Others show evidence of black hole jets triggering new star formation in specific regions. One of the most dramatic examples of black hole feedback can be seen in galaxy clusters. These are massive collections of hundreds or thousands of galaxies held together by gravity. At the center of these clusters, there's usually a giant elliptical galaxy with a supermassive black hole at its center. These central black holes are some of the most massive objects in the universe, with masses that can reach tens of billions of suns. And they're incredibly active. The jets from these black holes can extend for millions of light years, far beyond the boundaries of their host galaxies. These jets plow through the hot gas that fills the space between galaxies in the cluster, creating enormous cavities and shock waves. This has a profound impact on the entire cluster. The hot gas between galaxies is the raw material for future star formation. When the central black hole heats up this gas and pushes it around, it affects star formation in all the galaxies in the cluster. In some cases, it can completely shut down star formation across the entire cluster. This is cosmic engineering on the largest scales imaginable. A single black hole can influence the evolution of hundreds of galaxies spread across millions of light years of space. It's like having a single construction foreman directing the building of an entire city. But perhaps the most amazing thing about black hole feedback is how it creates the perfect conditions for life. Without black holes regulating star formation, galaxies would burn through their gas supplies too quickly. They would form all their stars in a massive burst early in their lives and then become dead, sterile collections of old stars. Instead, black hole feedback stretches out the star formation process over billions of years. This creates a steady supply of new stars throughout the galaxy's lifetime. And new stars are essential for life because they create and distribute the heavy elements that planets and life are made of. Our sun is a perfect example of this. It's what astronomers call a second or third generation star, meaning it formed from gas that had already been enriched with heavy elements by previous generations of stars. Without the regulated star formation that black holes provide, our sun might never have formed, or it might have formed in an environment without the heavy elements necessary for planet formation. So, in a very real sense, we owe our existence to the black hole at the center of our galaxy. Not just because it helped create the conditions for our sun to form, but because it has been maintaining those conditions for billions of years, ensuring a steady supply of new stars and the elements they create. Now, let's talk about how astronomers figured all this out. The connection between black holes and galaxies wasn't obvious at first. Black holes themselves are invisible, so detecting them requires looking for their effects on nearby matter and light. The first clue came from studying the centers of galaxies. Astronomers noticed that stars very close to galactic centers were moving incredibly fast, much faster than could be explained by the visible matter in the galaxy. This suggested there was a massive invisible object at the center providing the extra gravitational pull. But the real breakthrough came when astronomers started measuring the masses of these central black holes and comparing them to properties of their host galaxies. They found that tight correlation I mentioned earlier between black hole mass and the mass of the galaxy's central bulge of stars. This correlation is called the M-sigma relationship, where M is the mass of the black hole and sigma is the velocity dispersion of stars in the galaxy's bulge. The relationship is remarkably tight across galaxies of all sizes, from small dwarf galaxies to massive giant ellipticals. The tightness of this relationship tells us that black holes and galaxies must be closely connected throughout their evolution. If they evolved independently, we wouldn't expect to see such a precise correlation. It's like finding that every person's height is perfectly correlated with the size of their shadow. It tells you that the two things are fundamentally linked. But measuring black hole masses isn't easy. Astronomers have developed several clever techniques to do this. For nearby galaxies, they can track the orbits of stars very close to the galactic center. The faster these stars move, the more massive the central black hole must be. For more distant galaxies, astronomers look for the signatures of active black holes. When a black hole is actively feeding, the hot accretion disk around it produces characteristic patterns of light. By analyzing this light, astronomers can estimate the black hole's mass and how fast it's consuming matter. These observations have revealed that black holes and galaxies grow together throughout their lives. When a galaxy is young and gas-rich, its central black hole feeds actively and grows rapidly. As the galaxy ages and uses up its gas supply, the black hole becomes less active and grows more slowly. This coevolution explains why we see such a tight relationship between black hole masses and galaxy properties. They're not just correlated by coincidence. They're correlated because they've been influencing each other's growth for billions of years. Computer simulations have been crucial for understanding this process. Modern simulations can follow the evolution of galaxies over billions of years, including the effects of black hole feedback. These simulations show that without black hole feedback, Simulated galaxies look nothing like the real galaxies we observe. In simulations without black holes, galaxies form stars too efficiently. They quickly turn all their gas into stars and then stop forming new stars entirely. The resulting galaxies are too small, too dense, and too red compared to real galaxies. But when the simulations include black hole feedback, everything changes. The simulated galaxies form stars at a more measured pace, maintaining gas reserves for future star formation. They develop realistic structures like spiral arms and central bulges. Most importantly, they match the observed relationship between black hole mass and galaxy properties. These simulations have also revealed some surprising details about how black hole feedback works. For example, they show that the timing of black hole feedback is crucial. If feedback kicks in too early, it prevents the galaxy from forming enough stars. If it kicks in too late, the galaxy forms too many stars before the black hole can regulate things. The simulations suggest that nature has found a sweet spot where black hole feedback kicks in at just the right time to create the diverse population of galaxies we see today. This fine-tuning is remarkable and suggests that the relationship between black holes and galaxies is one of the most important processes in the universe. Recent observations have started to reveal this process in action. Astronomers have found galaxies in the process of transitioning from active star formation to quiescent states, apparently due to feedback from their central black holes. They've also found galaxies where black hole jets are clearly interacting with the surrounding gas, either heating it up or compressing it to trigger new star formation. One particularly interesting discovery is the existence of galaxies with unusually massive black holes for their size. These galaxies seem to have experienced particularly strong feedback early in their lives, which stunted their growth while allowing their black holes to continue growing. They're like cosmic bonsai trees, kept artificially small by their overactive black holes. On the flip side, astronomers have also found galaxies with unusually small black holes. These galaxies seem to have avoided strong feedback, allowing them to grow larger than normal while their black holes remain small. These outliers help us understand the normal relationship by showing us what happens when things go wrong. The study of black hole galaxy connections has also revealed something unexpected about galaxy mergers. When two galaxies collide and merge, their central black holes eventually spiral together and merge as well. This process releases enormous amounts of energy in the form of gravitational waves. These black hole mergers can have dramatic effects on the resulting galaxy. The energy released can kick the merged black hole out of the galaxy center entirely, or it can trigger massive outflows that completely change the galaxy's structure. We're just beginning to understand these extreme feedback events and their impact on galaxy evolution. Looking at galaxy clusters has provided another window into black hole feedback. The hot gas in galaxy clusters can be observed directly using X-ray telescopes, and astronomers can see clear signatures of black hole jets interacting with this gas. In many galaxy clusters, the central galaxy's black hole creates enormous cavities in the surrounding hot gas. These cavities are like cosmic bubbles blown by the black hole's jets. The size and shape of these bubbles tell us about the power and direction of the jets over time. Interestingly, these bubbles seem to prevent the hot gas from cooling and falling into the central galaxy. Without this prevention, the central galaxy would continue growing by consuming the cluster gas, potentially becoming much more massive than what we observe. So, black hole feedback doesn't just regulate individual galaxies. It also regulates the growth of the most massive galaxies in the universe. This regulation has important implications for the formation of structure in the universe. Galaxy clusters are the largest gravitationally bound structures in the cosmos, and the galaxies within them represent some of the most extreme environments for star formation. Understanding how black holes regulate these environments helps us understand how structure formation works on the largest scales. The role of black holes in galaxy evolution also connects to some of the biggest questions in cosmology. For example, astronomers have noticed that the cosmic star formation rate has been declining over the past several billion years. The universe formed stars most rapidly when it was about 3 billion years old, and the rate has been dropping ever since. This decline coincides with a time when massive black holes were becoming more common and more active. It's possible that the increasing influence of black hole feedback is partly responsible for the universe's declining star formation rate. As black holes have grown more massive over cosmic time, they've become better at regulating star formation in their host galaxies. This connects to the question of what will happen to star formation in the far future. If black hole feedback continues to become more important over time, it could eventually shut down star formation entirely across the universe. The cosmos would then slowly fade as existing stars burn out without being replaced by new ones. But this is still speculative. We don't fully understand how black hole feedback will evolve over the extremely long timescales involved. New gas can still fall into galaxies from the surrounding cosmic web, potentially reigniting star formation even in galaxies with massive black holes. There's also the question of what happens when galaxies run out of gas entirely. In the far future, many galaxies will have converted all their available gas into stars or lost it to black hole feedback. At that point, the coevolution of black holes and galaxies will enter a new phase that we don't yet understand. These long-term questions highlight how much we still have to learn about black hole galaxy connections. Despite decades of research, we're still discovering new aspects of this relationship and new ways it influences cosmic evolution. One area of active research is understanding how the first black holes and galaxies formed in the early universe. Observations of very distant galaxies have revealed that massive black holes existed when the universe was less than 1 billion years old. These early black holes seem to have grown incredibly rapidly, possibly faster than their host galaxies. Understanding how these first supermassive black holes formed and grew so quickly is one of the biggest challenges in modern astrophysics. Did they form from the collapse of massive stars, or did they form through some other process? How did they manage to grow so fast in the early universe when matter was less dense than it is today? These questions are driving the development of new telescopes and observational techniques. The James Webb Space Telescope is already providing unprecedented views of the early universe, including observations of some of the first galaxies and black holes. These observations will help us understand how the black hole-galaxy relationship got started. Another frontier is understanding black hole feedback in different types of galaxies. Most of our detailed knowledge comes from studying massive elliptical galaxies, but black hole feedback likely works differently in spiral galaxies like the Milky Way or in small dwarf galaxies. Recent observations have found evidence of active black holes in galaxies much smaller than previously thought possible. These small galaxies might provide clues about how black hole feedback works in lower mass systems, and whether the tight correlation between black hole mass and galaxy properties extends to the smallest galaxies. There's also growing interest in understanding how black hole feedback varies with cosmic environment. Galaxies in dense galaxy clusters experience different conditions than isolated field galaxies. The hot gas environment in clusters provides additional material for black hole feedback to work with, but it also creates different physical conditions that might change how feedback operates. Understanding these environmental effects is important for building a complete picture of how black holes influence galaxy evolution across different cosmic settings. It also helps us understand why galaxies in different environments look different from each other. The study of black hole jets has become increasingly sophisticated as well. New radio telescopes can map these jets in incredible detail, showing their structure and how they interact with the surrounding gas. Some jets show complex structures with multiple components, suggesting that black hole activity varies on relatively short timescales. These detailed observations of jets help us understand the physical processes that launch them from black holes. The exact mechanism is still not fully understood, but it seems to involve the interaction of magnetic fields with the spinning black hole itself. This connects black hole feedback to fundamental physics in extreme environments. Computer simulations have also become more sophisticated, incorporating more detailed physics and following galaxy evolution over longer timescales. Modern simulations can model the formation of individual stars within galaxies while also tracking the large-scale effects of black hole feedback. These simulations are revealing that black hole feedback operates on many different scales simultaneously. On small scales, it affects the immediate environment around the black hole. On intermediate scales, it influences star formation across the galaxy. On large scales, it can affect entire galaxy clusters. Understanding this multi-scale nature of black hole feedback is crucial for predicting how galaxies will evolve in the future. It also helps explain why the effects of black holes can be seen across such vast distances, despite the black holes themselves being relatively tiny. The connection between black holes and galaxies also has implications for astrobiology and the search for life elsewhere in the universe. The regulation of star formation by black holes helps ensure a steady supply of heavy elements necessary for planet formation. It also helps maintain stable galactic environments over the long timescales necessary for life to develop. Different types of galaxies provide different environments for potential life. Spiral galaxies like the Milky Way might be particularly favorable because they maintain steady star formation rates and have relatively peaceful environments away from their active centers. Elliptical galaxies, which have often experienced strong black hole feedback, might be less favorable because they have lower star formation rates and different chemical compositions. Understanding how black hole feedback shapes these galactic environments helps us understand where in the universe conditions might be most favorable for life. This knowledge could guide future searches for potentially habitable planets and even help us understand how common life might be in the cosmos. The relationship between black holes and galaxies also teaches us about the interconnected nature of the universe. What happens in one part of a galaxy can influence regions thousands of light years away. What happens in one galaxy can influence other galaxies in the same cluster. These connections span vast distances and long timescales, showing us that the universe is much more interconnected than it might appear. This interconnectedness has philosophical implications as well. It shows us that even the most extreme and seemingly destructive objects in the universe play constructive roles in cosmic evolution. Black holes, despite their fearsome reputation, are actually essential for creating the kinds of galaxies where stars, planets, and life can thrive. The study of black hole galaxy connections continues to evolve as new observations and theoretical insights emerge. Each new discovery adds another piece to the puzzle of how these cosmic partnerships work and why they're so important for understanding the universe as a whole. Current observations are pushing toward understanding these processes in the very early universe, when the first galaxies and black holes were forming. Future telescopes will provide even more detailed views of these early epochs, helping us understand how the patterns we see today first emerged billions of years ago. There's also growing interest in understanding the detailed physics of how black hole jets interact with galactic gas. New computer simulations can model this interaction with unprecedented detail, showing exactly how jets heat gas, create shocks, and trigger or suppress star formation. These detailed studies are revealing that black hole feedback is much more complex than originally thought, It's not just a simple on-off switch for star formation. Instead, it's a sophisticated regulatory system that can fine-tune galaxy evolution in response to changing conditions. The implications of this research extend far beyond astronomy. The mathematical techniques developed to understand black hole feedback are being applied to other complex systems in physics and engineering. The computational methods used to simulate galaxy evolution are contributing to advances in high-performance computing and data analysis. Most importantly, this research is changing our understanding of our place in the universe. We now know that the galaxy we live in, and indeed our very existence, depends on the delicate balance between construction and destruction played out between black holes and galaxies over billions of years. This balance is remarkably precise. If black hole feedback were slightly stronger, galaxies would form too few stars to create the heavy elements necessary for planets and life. If it was slightly weaker, galaxies would burn through their gas too quickly, leaving little opportunity for the long-term stability that complex life requires. The fact that this balance exists and has been maintained over billions of years suggests that the universe is fine-tuned in ways we're only beginning to appreciate. Whether this fine-tuning is a remarkable coincidence, a result of natural selection among universes, or evidence of some deeper organizing principle remains an open question. What we do know is that the quiet partnership between black holes and galaxies has been essential for creating the cosmos we observe today. These invisible architects have been working behind the scenes for billions of years, shaping galaxies, regulating star formation, and creating the conditions necessary for planets, life, and ultimately for us to exist and contemplate these cosmic processes. The next time you look up at the night sky, remember that everything you see has been influenced by this partnership. The stars you observe, the patterns they form, even the chemical elements in your own body have all been shaped by the invisible black holes lurking at the centers of galaxies. These cosmic architects continue their work even now, quietly shaping the future of our galaxy and countless others throughout the universe. They remind us that some of the most important processes in nature are the ones we can't directly see, working patiently over timescales so vast they challenge our ability to comprehend them. But here's the most mind-blowing part of this entire cosmic story. Recent observations have shown us something that completely changes how we think about our own place in this galactic partnership. The black hole at the center of our Milky Way, Sagittarius A, isn't just some ancient relic sitting quietly in space. It's been actively influencing our corner of the galaxy throughout Earth's entire history. Scientists have discovered that major outbursts from our galactic center black hole, happening every few million years, actually coincide with some of the most dramatic events in Earth's evolutionary history. The timing isn't perfect, but it's close enough to be intriguing. Could the same black hole that helped create the conditions for life on Earth also be influencing the course of evolution itself? Think about the implications of this. The extinction events that wiped out the dinosaurs and paved the way for mammals to dominate the planet might be connected to activity from a black hole 26,000 light-years away. The ice ages that shaped human evolution might be part of galactic cycles driven by our central black hole. We're not just observers of this cosmic dance between black holes and galaxies. We're participants in it. Every breath you take, every heartbeat, every thought you think is happening inside a galaxy that has been carefully sculpted by its central black hole over billions of years. You are literally made of atoms that were forged in stars whose birth and death were regulated by black hole feedback. This realization transforms the entire story from an abstract astronomical phenomenon into something deeply personal. The invisible architect at the center of our galaxy hasn't just shaped the Milky Way, it has shaped us. So when we look at black holes now, we see something completely different from the cosmic destroyers they were once thought to be. They are the universe's master architects, working patiently over billions of years to create the perfect conditions for galaxies to thrive and evolve. They regulate star formation like cosmic thermostats, ensuring that galaxies don't burn through their gas too quickly while also preventing them from becoming stagnant and lifeless. They create and maintain the delicate balance that allows for the steady production of heavy elements necessary for planets and life. The relationship between black holes and galaxies is one of the most profound partnerships in nature. It spans vast distances and enormous timescales, connecting the smallest scales of physics to the largest structures in the universe. It shows us that destruction and creation are not opposite forces, but complementary aspects of cosmic evolution. Most remarkably, this partnership has created the exact conditions necessary for our existence. The regulated star formation in our galaxy, the steady production of heavy elements, even the stability of our galactic environment over billions of years, all depend on the ongoing influence of the supermassive black hole at our galactic center. We are not separate from this process. We are part of it. We are living proof that the universe's invisible architects have done their job well, creating not just galaxies of stars, but galaxies where those stars can nurture planets, life, and intelligence capable of understanding the cosmic processes that created them. The next time you wonder about your place in the universe, remember that you are part of an ongoing collaboration between black holes and galaxies that has been billions of years in the making. You are not just in the universe. The universe, shaped by its invisible architects, is in you. If this changed how you see black holes and our cosmic home, subscribe for more space stories that will shift your perspective on the universe.